Hey everyone, and welcome to this lesson on the response and explanatory variables and how to use scatter plots. This subtopic, fitting a linear model to numerical data, is actually huge, but mainly because it has to cover a lot of little points that can be checked off quite quickly. We're going to cover dot points 3.1.8 and 3.1.9, focusing on the response and explanatory variables and using scatter plots to display numerical data. Let's get straight into it. We've previously brought up response and explanatory variables. Sometimes within data, we notice a causative relationship. One variable causes a change in the other. A common example is the relationship between studying and test results. The more you study, the higher your test result will be. If it is the case where there is a causative relationship, there will be a response variable and an explanatory variable. As the name suggests, the response variable is the one that changes in response to the explanatory variable, and likewise, the explanatory variable is the reason for the change, or in other words, explains the change that occurs in the response variable. For those of you that do a science, the response variable can be thought of as the dependent variable and the explanatory variable as the independent variable. This data shows the number of hours spent studying mathematics by each student and their corresponding mark in a recent test. As we've been doing a lot in our lessons, plotting the data is a great way to visualize it, which makes it a lot easier to spot trends. To do this, you'll obviously require two axes, x and y. If you've identified a causative relationship between the variables, the x-axis should be the explanatory variable and the y-axis should be the response variable. Here we see the higher marks in the test correlate to more hours spent studying. In this scenario, the time spent studying is our explanatory variable and the test results are our response variable because we know studying for more time causes higher test results. To plot this data on a scatter plot, the x-axis will be the time spent studying and the y-axis will be the test results. Once your axes are drawn up and labelled, start plotting the points. Once all the points are plotted, the correlation becomes much clearer. Not only did the students that scored well spend more time studying, but the rest of the results suggest the more a student studied, the higher their result was. Using a class pad, we calculated the correlation coefficient for this data to be 0.999. Therefore, to concisely describe the association, we'd class it as a positive, strong linear correlation. To make sure you have a solid understanding of what the response and explanatory variables are, here are a few more examples. During summer, two common variables can be considered: the UV index and the intensity of sunburnt beachgoers. Days with a higher UV rating cause an increase in sunburn. This can be graphed with the UV rating of each day on the x-axis and the sunburn percentage on the y-axis, because we know the UV radiation is causing the sunburn. A second example could be the temperature of the water in a kettle at different points in time. The longer a kettle boils, the hotter the water inside gets. The time the kettle has been boiling for is the independent variable, and the temperature of the water is a dependent variable. We hope you found this short lesson useful and have a better grasp of exactly what the different types of variables are within causative relationships. In the next lesson, we'll be looking at how the line of best fit can be used to algebraically predict results from data.